AP 120, Chapter 2. The topics are ions and chemical bonds. So, when we look at the model of the atoms, we see that the electrons are out orbiting around the nucleus. And it turns out the electrons are not all in one clump. Instead, they're broken up into what are called shells or energy shells. These energy shells are discrete locations at different distances from the nucleus. The first energy shell has a maximum capacity for 2 electrons. So when we look at hydrogen, it has 1 electron in the first energy shell. The helium has 2 electrons in the first helium energy shell and is therefore complete. And so if a third electron shows up, so for lithium there are 3 electrons, then that third electron is in the second energy shell. All of the other energy shells hold a maximum of 8 electrons. At least that's how we're going to deal with it for this course. So that means lithium has 1, and then we can go all the way up to sodium here. Sodium has 8 in its second energy shell, and then it has 1 additional electron, so that additional electron number 11, is in the third energy shell. So again, 2 in the first energy shell, 8 in all of the other energy shells. Now, when we look at the periodic table, this will tell us how many energy shells an atom has, and also how many electrons are in the outermost shell. So, if we look at the rows, we see that these show how many energy shells the atom has. So, row 1, we have hydrogen and helium that have only 1 energy shell. Row 2, we have lithium through neon. Those atoms have 2 energy shells. Row 3, sodium through argon. Those have 3 energy shells. And then 4 and 5 and so on. So the rows will tell you how many energy shells the atoms possess. And then the columns going up down will tell us how many electrons are in the outermost shell. So in the first column, all of these atoms have 1 electron in their outermost shell. In column 2, all of these atoms have 2 electrons in their outermost shell. We skip this stuff in the middle, and then for column 3, they have 3 electrons in their outermost shell. Column 4 has 4, 5 has 5, so on, all the way down to the last column, which has its outermost shell fully complete. So that means they have 8 electrons in their outermost shell, except for helium, which only has 2. And these, in this final row, are referred to as the noble gases. Noble gases. All the other elements wish they could be like the noble gases. And the noble gases are basically chemically inert. All right. So this is important because the number of electrons in the outermost shell determines the chemical properties of the element. So helium has a complete outermost shell, so it is chemically inert, while hydrogen has 1 in its outermost shell. Lithium also has 1 in its outermost shell, so they are very, very reactive. Very, very reactive. So when we look, let's do a little practice run of using the periodic table to determine information about an atom and an element. So this element here is beryllium, Be for beryllium. How many protons does beryllium have? How many shells does it possess? And how many electrons are in the outermost shell? Well, I hope you came up with these numbers. 4 protons because 1, 2, 3, 4, its atomic number is 4. Number of shells, 2 because it's in the second row. Number of electrons in outermost shell, 2 because it's in the second column. Let's try again with silicon here. Si for silicon. How many protons? How many number of shells? How many electrons in the outermost shell? Hopefully, you came up with these numbers. 14. Its atomic number is 14. It has 14 protons. Number of shells, 1, 2, 3. It's in the third row, so it has 3 energy shells. How many electrons in the outermost shell? 1, 2, 3, 4. It's in the fourth row, so it has 4. I'm sorry, it's in the fourth column. Because it's in the fourth column, it has 4 electrons in its outermost shell. All right. Elements that have only 1 or 2 electrons in their outermost shell tend to lose those electrons. And elements in columns 6 and 7, where they have 6 to 7 electrons in the outermost shell, they tend to gain electrons. And the point of losing electrons and gaining electrons is to become like the noble gases. So these elements will lose 1 or 2 electrons, now having their outermost shell fully complete, similar to the noble gases, and these elements will gain 1 or 2 electrons, making their outermost shell complete, thereby making them similar to the noble gases, because everybody wants to be noble. Now, when an atom gains or loses electrons, it becomes an ion. So an ion is a charged atom. And if you lose electrons, then that is a positively charged ion, or a cation. So now has more protons than electrons when they lose electrons, so they are positively charged. When you gain electrons, the ion is negatively charged. So gain extra electrons, now there's more electrons than protons, so it is negatively charged. So that ion is an anion, a negatively charged ion. And it turns out that oppositely charged ions attract. So electrochemistry, opposites attract. So these positive ions are attracted to the negative ions and the reverse. And this allows for something called ionic bonding. Ionic bonding is a type of chemical bond, again, where oppositely charged ions are attracted to each other. And it occurs via what I refer to as electron adoption. So here's sodium. Sodium has 1 electron in its outermost shell. Here is chlorine atom. Chlorine has 7 electrons in its outermost shell. So that electron in the outermost shell of sodium leaves sodium and is adopted by the chlorine. Now we have a positively charged sodium ion, a negatively charged chlorine ion. They then have an ionic bond because of that attraction, and they become the compound sodium chloride. So 1 sodium atom, 1 chlorine atom becomes sodium chloride, which is actually salt, normal table salt. So we now have 1 sodium chloride molecule. Molecule? Oh yeah, molecules. You know that already. Molecules are when 2 or more atoms are bound to each other in some form of chemical bond. So again, adoption. Electrons leave 1 atom, go to the other atom. Now they're charged ions, and they form that ionic bond. And frequently, these ionic bound molecules form crystal arrays. So when you look at your salt, when you pour it out, you see this in little cubes, little crystals. And it is a pretty amazing process. As we know, sodium by itself, that element is extremely reactive. It will explode in the presence of air because of the moisture in water. Chlorine by itself, that element is a toxic gas that will kill people. But with this simple ionic bond, they become a molecule, sodium chloride, that is safe for us to consume. Pretty amazing. All right, another kind of chemical bonding is covalent bonds. Covalent bonds is electron sharing in order to fill the outermost shell. So here we have 2 hydrogen atoms, each with 1 electron in their outermost shell. Each wants 1 more electron, so they will share their electrons. So now they both have 2 electrons, and this forms a hydrogen molecule. 2 hydrogen atoms bound together by a covalent bond. And this is a single bond because they're only sharing 1 electron with each other. Now, you can also get a double bond or 2 covalent bonds between 2 atoms. So with oxygen, they share 2 electrons each, and giving us molecular oxygen. And then nitrogen, allows for a triple bond, so it shares 3 electrons between each of the 2 atoms, giving us molecular nitrogen. This is a triple bond. Again, giving us stable conformation because of the complete outermost energy shell. And these happen to be nonpolar molecules. They are nonpolar because they have the electrons and the charge distributed evenly between the atoms. And so they do not have a net uneven distribution of charge. Instead, it is evenly distributed. Now we have, say, carbon. Carbon, nitrogen, these guys in the middle often are involved in covalent bonds, sharing electrons. So how many electrons does carbon need to become stable? Well, it needs 4. It needs 1, 2, 3, 4. To become neon, it needs to now have 4 more electrons in its outermost energy shell. And when it does covalent bonding, like any covalent bonding, it is shared custody of those electrons. So here is carbon, and it is sharing 1 electron with 1 hydrogen, another electron with another, and so on and so forth, so that we have 1 carbon and 4 hydrogen atoms, all coming together to form methane. Here's a sort of bubble view of methane. So we have 5 atoms forming 1 molecule, a methane molecule. And it is nonpolar because this is an evenly symmetrical distribution of the electrons, so there's no uneven distribution. It is nonpolar. However, you can get a polar distribution. So water, H2O, where you have 1 oxygen and 2 hydrogens, each sharing their 1 electron with the oxygen. We get a lovely stable molecule, but it's uneven. The oxygen hoards the electrons, so the electrons spend more time around the oxygen than around the hydrogens, and this gives a uneven distribution of charge, so the hydrogens are slightly positive and the oxygen is slightly negative. The electrons are being shared unevenly. And this then allows for a third kind of bonding, hydrogen bonding. Hydrogen bonding is a weak bond, and it is between slightly positive hydrogen ions in a molecule being attracted to slightly negative oxygen or nitrogen atoms in other polar molecules. So here we have all these water molecules. They are all polar. Slightly negative oxygens are attracted to the slightly positive hydrogens. Slightly negative oxygen to the slightly positive hydrogen. This is a weak bond, relatively easy to break. So I think of it more as dating. And because of hydrogen bonding in water, we can see certain things like how water has what seems like a film. The water molecules are all attracted and holding to each other, so you can actually pour water in a glass and it'll go above the surface of the glass to a point. And this cohesion also allows things like insects to stand on top of the surface of water. So a lot of special chemical characteristics of water are caused because of this hydrogen bonding between the polar water molecules. And that is it for this part of the Chapter 2 lecture.